You're welcome to stop whenever you want to. So, but I'll just say like 10 minutes before 4:45. So
sounds good. I don't want to, because I'm getting tired. They're getting tired. So
yeah. It's you can feel the
exactly.
This is all extra time.
Yeah, and also I like them to be engaged. And if they're not engaged, then
so you can,
sounds good. Sounds good. Yeah.
All right. Okay, great. So, Alex.
Hello, everyone. To the second part of the first lecture, I guess. I know that you're getting a little bit tired, so I will. This part will be very notation heavy, so I will make you fall asleep. But this notation will be useful, so maybe pay some attention. So, what was the problem that we were solving earlier? I mean, we were talking about the toric code from the more quantum error correction side, and the problem that we were looking at is this problem of decoding. That I give you some syndrome, or some location of excitations, and you want to get back to the ground space without introducing a logical operator, right? So this problem is relevant because if we have a quantum computer, we need to monitor whether some errors are introduced, and if they are introduced, we need to remove them, and new errors will be introduced. So we've got to do it computationally efficiently. So that's why we care about this decoding problem. But like this is a difficult problem. So what I propose is the following solution. You know that you can move those excitations by applying a string-like logical operator. So how about we move them all in the middle? Since there is even number of them, they will annihilate. We are back in the code space, right? So this is a solution, right? This would be a decoder. Would that be a good decoder? Why wouldn't it be a good decoder? Because the environment could introduce like a string error that kind of goes around that way. And what I would do is I would just move it like that, and I would introduce an error. So it would be pretty bad. But is this such a stupid idea? Actually, it's not, because what I can do is I can first go back to the code space, and then what I guarantee. So I guarantee that I'm back to the code space, but I might or might not implement a logical operator, right? So in my case, if I consider just Z errors, I may introduce either this Z1 logical or Z2 or both or nothing. There's 4 options basically. I could have done trivial logical operator. I could do Z1. I could do Z2, or I could do Z1, Z2. So if someone told me what logical operator I implemented, I would be done, right? Because I just bring them back and I apply this logic operator, and then the action on the logical space is trivial. So that's perfect. So we can just use machine learning to tell me what is the label, right? And actually, one can apply machine learning techniques. Basically, you have this simple, call it pre-decoder, which brings you back to the code space. And then you train your neural network, say, on this configuration of syndromes to get the label. Whether I implement a logical identity, logical Z on the first qubit, on the second, or both. Anyway, that's just like a side remark that I wanted to make regarding decoding. Well, because you don't know how to solve the problem, so you throw machine learning at it, and it actually works. So isn't that nice? Because I will be telling you about like some other things that are tedious, and why should we think about it, right?
But why not do what you suggested? Denial of the shortest.
That's right. That's the rest of the lecture will be on that. Yes. But there we have to think harder. Here we just throw machine learning techniques at the problem, right? And then one conceptual simple observation, but like in the first machine learning papers about this problem, this was not pointed out. Basically, this simple pre-decoder that brings you back to the code space reduces this learning problem to just learning the logical label. Because initially they were learning the error configuration, but no one cares about error configuration because we only care about equivalence classes of errors. Okay, so but let's get back to less fun. Okay, so this is one remark about decoding. The other one I want to make is about significance of thresholds and what it means, because I was trying to get to that in my previous lecture, but I never got there. So okay, so I have this story code, whatever, L by L, and I know that it has distance d, which is the lattice size, right? That's the shortest string. And now let's assume that I have this phase flip noise. So it's an IID noise with probability p. So I can ask, what is the logical failure? What is the chance that the noise implements some error, and I try to undo it, but I end up implementing a logical operator. So this probability of failure typically would scale like p to the d, or maybe d over 2. And this depends on the decoder and the noise model. If I have erasures, it would be just d. If I have some phase flip errors, unknown locations, then it would be d over 2. But the point is that the scaling would be exponentially suppressed in d. So if I were to get better logical error rate, suppressed logical error rate, because I build this surface code 10 by 10, and then I get this logical failure of 10 to the minus, I don't know, 8, for instance. But I want to run an algorithm that has 10 to the 15th gates. This logical error rate would be too high. I would need to go down to 10 to the minus 15th. How do I get there? Right. One approach would be just to reduce p, because if I have a smaller error rate, then my logical error rate also goes down. But this requires improving my hardware, and we don't want to do that. We want to get our noisy components to be fairly reliable, but not ideal. So the other way to get to very low error rates would be to scale system up, and basically that's where this idea of the threshold enters. Does this make sense? So imagine you want to run an algorithm, a useful algorithm, and there are recent works. This is a very active area of research. We want to quantify how many gates do we have to implement in order to run some meaningful quantum algorithm that tells us, about some energy levels of some molecule or whatnot. Estimates typically tell us that you've got to do 10 to the power of 12, 15 basic operations. So, and one operation at a time. So if the probability of a failure of each operation is not comparable, like if you have some number of operations, and they can all fail with probability, right? So if every operation can fail with probability p, and you have n of them, if this is close to 1, then the chances that your algorithm fails are basically 100%. So your p has to be at least at the order of the number of operations that you want to do. Oh, because I want to do 10 to the 50th operations, right? Yes. So of course, if I do just say 1 million operations, I'm perfectly fine. There's no problem about that. But you cannot do anything meaningful on a quantum computer if you have, say, just 1 million T-gates. Now, yeah, and if someone tells you otherwise, they either, they will either be billionaires or they don't know what they're talking about. So this is the error rate, or the error rate on the logical qubit, right? We use our toric code. We have physical qubits, and with that we engineer a logical qubit, and using that logical qubit we will run some algorithms, right? And I want the quality of my logical qubit to be very, very low, at the order of 10 to the minus 15. Or something like that. And for instance, by building the surface code patch, 10 by 10, with 100 physical qubits, I can only get to, say, 10 to the minus 8. I'm saying that, if I run an algorithm with 10 to the 15th gates, that's not good enough. That is because if you have IID noise, and it happens with probability p that Z error happens, IID. So it's identical, independent and identically distributed, meaning the environment at each location can implement Z error with probability p. That's right. That's right. And this is also the significance of the distance. You guys were asking earlier about. Mm-hmm. That's right. So it would be probably, so this is just memory, but like if you lose the preserving your information, you're not gonna get away with running logical operations. So this is just a hand wavy. Wait, this is just an introduction to threshold, right? So notice that the environment by itself can just implement a string. What would be the probability of that? Well, it would be like p to the power of d, roughly, right? So the environment by itself can implement a logical operator, and then I'm already done. I cannot undo it. So my failure would be at least of this order, right? Okay, so
isn't there a trade-off that if you increase the system size, you need to the logical operation will belong, like the weight of logical operator.
That's right. But what do you mean by weight?
The logical operator would be like the string of C.
That's right, but that is what we want to do, because the environment may implement that. We want to protect that. But and we don't care about that we need to apply Pauli X along this line, because we can control, we can address every qubit. So this is not a problem for us. This is a problem for the environment. That's basically I'm getting there. So stay tuned. Okay, but like with those thresholds, let me tell you what we're after. So when I have system size, why is it non-trivial? If I have the toric code L by L, then I have L squared qubits, and if every qubit is affected with probability p by an error, then the average number of errors is P times L squared, okay? But what does the Torah code tell me? You know, there's the distance L. So what I'm guaranteed to handle is only I'm only guaranteed to be able to successfully correct the number of errors that is upper bounded by distance minus 1 over 2 floor. So this is L over 2. So what the threshold tells me is if I consider bigger and bigger toric codes, you know, I can handle a number of errors that scales as L squared on average. Whereas, you know, if the environment was adversarial and was applying, you know, some errors in some particularly nasty configurations, I would be only able to tolerate L. Does this make sense? This is like floor. So it's the biggest integer, not than d minus 1 over 2. Here. That's just floor. Sorry. And this is L over 2. Sorry. This is. So guaranteed means if the environment, if the adversarial environment can act on certain number of qubits, any qubits, then, you know, if I allow the environment to act only on that many qubits, at most that many qubits, then I can always correct, because that's the definition. That's the definition of the distance.
It's possible that the environment did this and you decided to do that.
But then it would be so I can always, if the environment acts on at most
That's why you have
d minus. That's right. That's right. That's okay. So with this threshold thing, let me just add. I want to, because I'm off the script totally, but what I want to mention is, yeah. So basically the statement of the theorem is to say that the toric code has a threshold. I mean, let's make it slightly more precise, because we always say it, but like, what do we really mean, right? So in order to make such a statement, I need 3 components. So I need a code family. That is parameterized by some number, for instance, L. L is, you know, there's no difference for the toric code on the square lattice, but, you know, L I use to kind of parameterize the lattice. D is just, you know, code quantity. I mean, D is the code distance, right? And D equals L. So but then you would, you know, in order for them to move apart, you would need to apply more and more errors. So this guy would grow, right? Yeah. So it's not that, you know, I take like a snapshot, you know, and then so I started with the ground state. You know, the environment, you know, created some configuration, whatever, and, you know, the number of operators that were applied is, you know, the number of errors, right? It's not like that. Yeah. But let me get to, because, you know, let me get to those thresholds, you know. So to talk about the threshold, we need 3 components. One is we need to specify a code family And if we have a code family, we have individual codes in this family, and they will be parameterized by some parameter L. The meaning, since I'm talking about the toric code family, the meaning of L here is the linear system size, and it happens to be matching the distance of the toric code on lattice L by L. All right. So I hope now this is clarified. The second component that we have is we need to specify a decoder, the decoding algorithm. So for instance, we can use this machine learning decoder. That's a perfectly valid decoder. We can use the minimum wave perfect matching decoder that I briefly sketched in the previous lecture, or the RG decoder. We can use them here. And the third component that we need is we need to specify what noise we have. And then, we can have the IID noise, meaning each qubit is affected independently on other qubits. And, say, bit flip noise. And then we say with probability P, each qubit is affected, okay? Once we have those three components, we can make a statement. We can say, we can have the following theorem for the toric code, for instance. So for the toric code family and minimum wave perfect matching decoder and bit flip noise with error rate P, there exists some constant P star, and that is non-zero, such that for every P, the error rate that is smaller than P star, probability of successful correction will go to 1 in the limit of L going to infinity. Meaning, if I consider larger and larger system sizes, the probability that I apply the decoder, and the decoder together with noise implements some non-trivial logical operator, this failure rate would go to 0, or the probability of success would go to 1. That's what can be proven rigorously. You don't require how it goes to 1. But typically it goes to, for the toric code, it goes exponentially. Yes.
This depends. P star depends on noise and decoding.
So it depends on all those three components, right? Because I can consider the toric code on the square lattice. I can consider the toric code on triangular lattice, or yes. So, but and typically, oftentimes you hear in conversation, oh, a toric code has threshold like that, and those statements are kind of meaningless unless you clearly specify those three components.
What doesn't? How do you violate this if P star is 0? How do you violate?
Well, for instance, you can consider the Bacon-Shor code, and there would be no threshold. Yeah, because the reason why it's non-trivial is what I wrote here. The toric code is guaranteed to correct only the number of errors that scales linearly in L. But it operates in the regime where the number of errors that you have is L squared. So you basically use your code in the regime where it's not designed to work, very roughly speaking. That's why, this is not a trivial statement, right? You basically use something that is designed, to work somewhere, and you put it way beyond the regime of applicability, but it still works. If your noise has this structure, because, I could equally well assume some noise that, introduces long Pauli strings. And then I would have no threshold. That's right. For instance, if you use just a simple pre-decoder without this label, it would have 0 threshold. No. So you can have bit flip, phase flip, depolarizing noise, or some other coherent noises. So here I just gave you an example. So you just need to specify noise. Right. So you tell me, how, what type of noise is applied to my system. But it's not that for any noise this is true, right? Because if I had some correlated noise, I could concoct a noise that with probability, small probability implements a logical Pauli error, and that's it, right? Well, so this noise is, there's some parameterization of the noise, so some noise strength, yes. So and then it means that if this noise strength, is below certain value, I can reduce the logical error rate by just scaling up my system. So it's more like, you give me noise, I prove that there's a threshold. Typically, you consider IID noise, which is acting independently of. Yeah, and then there would be there may be no threshold, right? So you're basically bringing me with your question to the next point that I would want to make, which is you can prove certain things, but maybe you don't know how to prove things. So you can always test it numerically, for instance. So
this is the with high probability statement. It's not for the worst case, right? Because the worst
That's right. So, but this is with high probability, which is probability of successful correction goes to 1.
numerical simulation will not give you the.
Yes. So, but what do you do? So, if you want to estimate, the Torah threshold, with some decoder, you just implement things, but then you can implement your decoder on some. So what you're gonna plot is you're gonna plot this failure, probability of a failure, as a function of noise strength P. And for some system size L1, I would get basically such a curve. The smaller P, the smaller the logical error. But now I can consider a system size that is larger, L2. And what I will see numerically is that the curve is steeper, the decay is steeper, and so on and so forth. If I have like small one, L0, this is what I typically see in the numerics. And it happens to be, that if we eyeball such a plot, the point where they intersect, this would be my estimate of the threshold. And because, in the limit of very large system sizes, it would be some sort of a step function. Good? Okay. So now fun's over. Let's get to the formulas. So, so far I was like hand wavy and trying to give you some intuitions and stuff. But what would be useful for us when we talk about the Torah code or more general constructions is to introduce this notion of a chain complex. And I will introduce the chain complex that is associated with cellulations of two-dimensional manifolds. So what is it like? Let me be pictorial to a certain degree. So let's consider some lattice. It can be a square lattice. I can now consider F2 linear vector spaces. Okay, let me start from the beginning. So a cellulation, a lattice. What is it? So it is basically a triple where I specify vertices, edges, and faces. Okay, this is the structure that I have. It's a discretization of some manifold, for instance, of a torus. And now I consider the following object, C2 partial 2, C1 partial 1, C naught. So I consider a sequence of F2 linear vector spaces, and the basis of this vector space is C2 is faces of the cellulation that I have, C1 is edges, and C naught is vertices. You know, the indices of those vector spaces capture the dimensionality of the object I work with. Okay, this is the definition of this chain complex, or rather those vector spaces, but how should you think about them? Well, vector spaces, their elements are vectors. What are the vectors in those vector spaces? Here, basically, any vector in this vector space is some subset of faces. It's Z2, it's F2 linear, yes. So there is this one-to-one mapping between elements of those vector spaces and subsets of my faces. The vectors in this vector space would be subsets of edges. And similarly here, subset of vertices. Linear combinations. Yeah, so the basis, that's right. So now my basis, you know, would be, so any vector would be expressed in this basis, and the coefficients are 0 or 1. So this gives me, you know, the subsets. Does this make sense? So, you know, an element, for instance, in C2 would be this guy, and this guy. So I can think of it as, you know, a bit string that has ones here and zeros everywhere, right? I just, you know, I can think of those vectors, those elements in those vector spaces as formal sums of faces, right? With Z2 coefficients. And now what are those guys? Those guys are linear operators called boundary operators. And I think I don't need to define them anymore, right? If I say boundary operators, what could they give you, right? They give you a boundary, right? So if I apply a partial 2 on the face, what does it give me? It's boundary, right? But this should be understood as this guy plus this guy plus this guy plus this guy, right? So if you give, yeah, if for any vector, you know, I would just, so what would be the boundary operator of, you know, say 2 adjacent faces? Well, I would include this edge once, these edges once, but this edge would be included from this face and from that face. So it would be included twice, and it's, you know, modulo 2, so it would not be here. So it would give me really this elongated shape. Okay, so it's very intuitive. And similarly, partial 1, you know, acts on edges, and it just gives me the endpoints, right? Because it's Z2, so I don't have to worry. Yes, that's right. But that's right. But here I don't care. That we may have to worry about orientation. If I didn't have Z2, I would worry about orientation. So my vector spaces would not be over Z2. So I would have, yeah, I would need to, yeah, I would need to worry about, like for instance, I would have some. Let me not get into those details because I will not worry about that at all. So because we work with Z2 chain complexes, and this is all that we have in the context of quantum error correction. Let me not go into that. Okay, so I told you that this chain complex is a structure that arises from some discretization of a two manifold, but it doesn't have to. This can be abstractly, it could be any sequence of vector spaces with linear operators between them that satisfy the following condition. Boundary of the boundary is 0. Right? So in this geometric picture, this condition is trivial, right? And it says that the boundary of a boundary is trivial. And how do you see that? Well, if I calculate the boundary of the square, it's a boundary, but there are no dangling vertices. So but in general, to have a chain complex, I can have any vector spaces and linear maps between them that satisfy this condition. Okay. So let me use some nomenclature. So I can ask what are the one chains. So I would call the elements of this vector space one chain, or subsets of edges. What are the one chains for which their boundary is 0? So it can be phrased as what is the kernel of this boundary operator? So this is this is called cycles. And you can think about the elements here as loops. And here, when you think about loops on a torus, you can differentiate between loops that are contractible and loops that are non-contractible. And this differentiation comes from considering the following objects. So I can also ask what are the cycles that are the boundaries of higher dimensional objects, right? So I can consider image of partial 2. Those would be those I call boundaries, or if you want to be more precise, one boundaries, right? Because those are one-dimensional objects. Those would be one cycle. Great. Now, notice this trivial inclusion. Any boundary is a cycle. Why is that? Well, because of this condition, right? Because if I have some object, if I have epsilon that belongs in image of partial 2, this is equivalent to having omega that is in C2 such that the boundary of omega is epsilon. So now if I apply partial 1 to epsilon, this is partial 1 applied to partial 2 applied to omega, and this is the 0 operator. So this is 0. Right? So this is a very short proof that every boundary is a cycle. Okay, so now I can imagine considering quotienting, taking a quotient of right, but there could be cycles that are not boundaries, and those would correspond to those non-contractible loops, right? Because boundaries, can be thought of as contractible loops. The cycles that are not boundaries would be non-contractible loops. So now I can consider a group H1 called the first homology group. That is the quotient of kernel partial 1, image partial 2. So I basically consider equivalence classes of cycles where the equivalence relation is up to boundaries. You got lost here. Okay, so here what I showed is the following: boundary, any boundary is a cycle. Oh. Yes, so epsilon belongs in image of partial 2 if and only if there exists omega in C2 such that partial 2 of omega is epsilon. Right? That's right. That's right. Yes. Yeah. That's right. So this is the condition that we have. Boundary has no boundary, and this is a proof. Yeah, we kind of. Yeah, it's yeah, but just to yeah, it's pretty trivial. I agree. But so what do we do here? We consider this first homology group that is basically we don't worry about. So we have some loops and we can deform them, right? Because we have the equivalence relation up to boundaries. So if I had some cycle that is like that, an equivalent one would be obtained from this one by adding some some boundary. So this would disappear. So this is just intuitively it's just deforming loops, but this guy would not be equivalent to the guy that is like wrapping around the torus.
I can understand why if you are on torus can't also put practical loops. Can't they be boundary? Like if I think of a ring of faces around the.
So this is something to think of. You should think about it. So if I have one loop like that, this is not a boundary. But if I have two loops, it's a boundary, right? Because I can fill it in. So homotopy would be. That's right. That's right. They would basically be very related.
Is there anything else in this H1 other than the different types of dot track we have?
No.
Isn't that the same as the
It would correspond to it would be very related.
You need to go to genus 2. You need to go to genus 2. There is a contract that is trivial. You need to go to genus 2 for them to be different.
Because you would be like
The group is not a group.
Is homology the affiliation of
yes, you can consider relative homology, and then basically you would have your chains can terminate. There would be yeah. So there's it's called relative homology. That's right. That's right. You could use these formulas. Yes. So okay. So this is some jargon, some formalism, but where do we have the torque going? So the torque code can be defined by identifying those three vector spaces with Z stabilizers, this with qubits, and this with X stabilizers. And this should make intuitive sense to you because those are faces. Our Z stabilizers were associated with faces. Our X stabilizers are associated with vertices. Qubits were associated with edges. And I guess the so now if I have some element in this vector space called omega, this would correspond to Z times Z-type stabilizer, and the support of this Z-type stabilizer would be could be calculated as partial 2 applied to omega. So the boundary of that guy, right? And intuitively it's clear. If I take the stabilizer that corresponds to those two faces, what is its support? It's basically its boundary. And the meaning, but now if I have some, so this is basically support of Z stabilizers. Stabilizer associated with omega, right? And if I have some Pauli Z error, if I have Z error on some subset of edges epsilon, then its syndrome, meaning the X checks that are violated, can be calculated as partial of epsilon. This would be syndrome of epsilon. And how do I see that? Well, if I have some subset of edges where Z errors happen, we were doing that earlier in the talk. The syndrome is the endpoints. This is the boundary of that object. And if you view those boundary operators as binary matrices, and if you view the vectors in those vector spaces as column vectors, then you could read off the support of your Z-type checks and X-type checks as correspondingly columns and rows of those matrices. So if you view this as a matrix, then those would be Z checks. They would denote the support of my Z checks. And if I view this boundary operator as a matrix, then its columns, in rows, sorry, would be the support of X checks.
I'm just wondering, vectorly, today we talked about surface code, and you can kind of like rewrite how this core code works. It looks like there's like an asymmetry between the Z stabilizers and X stabilizers here, and like how you set this up. But in like certain geometries, they're kind of like this.
That's right. So, so there's symmetry here. In a sense, I could consider Z stabilizers, qubits, and X stabilizers, to be like faces, edges, vertices. But now to view X stabilizer on faces, I would take the dual lattice. In this language, it would correspond to having a chain and a cochain. Cochain would go in the other direction, or whatever you want to denote it. And viewing those matrices as viewing those operators as matrices, those would be transpose matrices, right? So this symmetry would be restored. And okay, so that's basically the chain complexes, the toric code. And let me make an important remark that this chain complex can be any chain complex. And this construction that I identify Z stabilizers with this vector space, X stabilizer with that vector space, and the middle one with qubits. This construction describes any CSS code. The toric code structure, or the toric code construction arises if this chain complex is induced by some cellulation. Well, right. I mean, here I really don't worry about, and you shouldn't worry about that in the context of what we discussed, and to see that it's going to be zero. Those matrices, those operators would be defined as transposes of those operators. So if I had partial 1, partial 2 to be zero, then if I transpose this equation, I have 2 transpose 1 transpose is equal to 0, which tells me that composition of those co-boundaries is 0. Right, but that's how I define them. So I work only exclusively with Z2. I can think of them as binary matrices, and the condition they have to satisfy is that their product is 0. So the other direction is trivial because the other direction comes from the fact that if I transpose this equation, I get that equation. That's right. That's right. Call it a definition. Yeah. That's right. That's right. That's right. Right. Mm-hmm. That's right. That's right. That's right. That's right. Oh, they would be just this. So let's say that C2 is just a vector space where I have column vectors, and C1 is also column vectors, and C0 is column vectors, and there's some basis that labels my faces, edges, and vertices, and this binary matrix would basically each column of it would correspond to the support of the parity check. So if I labeled my guys, I don't know, 1, 2, 3, 4, this is the labeling of edges. This is my first face. Then the first column of this binary matrix would be 1, 1, 1, 1, and then the rest 0. It just encodes the support of the parity check associated with that face, and similarly for this guy. Right, and what Sagar was saying with this interpretation, cycles would be stabilizers and logical operators. Boundaries would be stabilizers. And now, if I take this quotient, I worry about stabilizers and logical operators up to stabilizers. So basically, this group captures, or rather, the elements in this group are different logical operators, and representatives in each equivalence class correspond to different implementations of the same logical operator. It would be, yeah. It would be a normal, yeah.
Meaning each one is a group.
It is a group. It is a group. And those are kind of by definition, because you know, they are defined as operators that have trivial syndrome. So kind of by definition.
Image of, you know.
Right. So this is just logical operators, and non-trivial logical operators. I would need to consider kernel partial 1 minus image partial 2. Those would correspond to non-trivial logical operators.
Image they reduce your space, the full Hilbert space to something. It's all those groups that are not stable.
That's right. Those would right, but yeah. But basically, if I have this object, let me just reiterate the message. This object, it can be God given. I don't know where it came from. Someone gave me this object. It's a sequence of vector spaces with those linear maps satisfying this composition condition. Then I can read off parity checks of my stabilizer code. And the parameters, right, and the basically this would correspond to the dimension of this. The dimension of this group would correspond to the number of logical qubits I have. And yeah. But I have this object, and then I get the CSS stabilizer code. Oh yeah, this is a quotient. This is set minus.
Make sure this corresponds only to the set of Z logical operators, right?
That's right. That's right.
So how do I see necessarily if I construct a similar group for X logical operators?
I'm not sure. I'm not sure. Yeah, I'm not sure. Yeah, I'll think about it. Any other questions? Oh yeah. So this chain complex is an object that that mathematically can be it doesn't have to be Z2, but what I care about is just Z2. This would give me some but like we work with qubits. Yeah.
Then there's other papers in the audience by over rings, and you get over U1 and rings, you get non-trivial what they call portion.
getting for qubits you don't have.
Okay, so I'm not sure how you guys feel about calculating more. That's right. Well, the commutation is encoded basically in this condition. And this definition that I gave you here, that parity checks are columns, of Z-type are columns, and here are rows. And then the fact that those two matrices multiply to 0 means that the overlap between any two vectors is even, that's commutativity. Yeah. Thanks a lot. I hope this is like somewhat instructive to you guys to get some intuition.